So to the actual tool, which is called the confidence interval for mu and how to compute it. Here it is. Okay. Let's begin. Now we talk about method boxes. So it's a specific, it's not a theorem, it's an actual method using the theory or the theorems to something practical. It says if we should use the right t-distribution to construct the confidence interval when we compute a mean. And the confidence interval is, well, we compute the sample mean. We have done that from the day one. We've done that in high school. We've done that in elementary school. We do it again. We compute the sample standard deviation. We may have done that in high school also, maybe even in elementary school. I'm not sure, but we could have. Now we put them into such a formula. This formula, unfortunately, is not taught to people in the Danish high school. It should, and we're trying to argue that it should in the future. But here it comes. Now you don't get it in high school, so you get it here instead. We take this standard error of the mean, as we've just saw, which was the theoretical sampling standard deviation of the mean, and I combine it with some quantiles from the proper t-distribution. Here is the t-distribution. It looks exactly like the standard normal. I take those quantiles, which has exactly half of alpha here and half of alpha here. And if all this alpha talk looks a bit problematic, it comes in a standardized version down here where we don't see this, but it, of course, here just repeats this part of the formula. And otherwise, we do see the rest, even though it gets a little bit squeezed there. If the most used interval is based on 95% confidence, and 95% confidence is exactly using the quantile. So we quantify the error, and we take the sort of the range, the 95% range of the error, and we use that to put the interval on and say, with 95% confidence, this is where we have the mean, right? So we use this knowledge of the variability and the uncertainty, where we have 2.5% to the left, and we have 2.5% to the right. Roughly plus minus 2, right? Roughly plus minus 2, sometimes a bit larger than 2, sometimes slightly smaller than 2, but roughly this is plus minus 2 standard errors. Example, and we've seen it now, so it shouldn't be too difficult. To use the formula, you need to work with a t-distribution. You need to have a feeling of what a quantile is when I talk about quantiles. So this is where you need to know about the stuff you were taught 3 weeks before coming here now. That a quantile, here, the number here, for instance, that would be, I could take this one, this is called t, this number here is called, yeah, well, that's called, I don't have to write again, it's called t subscript 0.975. It's the 97.5% quantile in this distribution. What is a quantile? That's the point that has 97.5% probability mass to the left of it and 2.5% to the right of it. That's the quantile. This quantile function exists in R. You might have met Q norm, but here is QT. It also exists. It tells us what is exactly the point on the distribution with 9 degrees of freedom. What would we get if we put Q norm instead? 0.975. Anyone who wants to throw a guess at this one? What would, applying the R function, Q for quantile, Q norm, without specifying any other options in the function call, to 0.975, what would R produce to us? Well, now you even have seconds enough to actually do it. What's the answer? Yeah, God damn it. The number, I told you, if you do, so you just, if he asks us a number, say 1.96 and he's probably happy. Because that's number one on the list of numbers to remember from this course. The number two, which exactly is 1.96. Understood the right way. But for the t-distribution, it's slightly larger, typically. What do you think you would get if you wrote qt 0.975, comma, and what if I had 100,001 observations? What would you get? 1.96, that's always the answer. Because for a large n, this t-distribution is exactly the same, at least up to 2 decimal points with this n. Probably I could go even much lower on the n, I just wanted to be sure here. Is the same as the standard normal, actually. So, nice. To the use of the formula. We compute the mean, we compute the standard deviation, we note what is the n, and I only have to read off, I have to find this t quantile. The only place I give you, I show you where to find those quantiles. That's within the R framework. As I've told you previously, it can be found many other places, these quantiles. These distributions are everywhere. Excel, whatever, MATLAB, anywhere. We use the R version here. In old statistical textbooks, you'll find those numbers in big tables at the end of the book. You'll find long lists of tables. Before we had the computer, people only had to look up those numbers in the table in the book, right? I mean, that's a bit old-fashioned. We can just ask the computer to provide that for us. And then we get the result that I already shared with you, an interval that we, with pretty high confidence, believes includes the true value for the mean height. That's the intelligence now. What's the time? Ah, there it was. Time disappeared on me. That's not a good feeling. Of course, we can do this in R. But I warn you again, please remember my stupid slide from the beginning with R cannot substitute your brain. You have to know the formulas. You need to know about the concepts and the meaning behind those formulas. And we're going to test you on that. So you cannot go through the course without actually knowing this. But of course, when you get to become the engineer that you're aiming for, you're not going to necessarily think about all those formulas so much. I mean, you need them to pass the exam, and they will sort of store in your brain and never go away again for the rest of your life. You will have this 2 standard deviations. As you find this nice TED talk by this brilliant mathematician. He says, if, just if, everyone had known plus minus 2 standard errors of the mean, the financial crisis would never have hit us the way it did. If people had just known about plus minus 2 standard errors. Either they didn't know or they didn't care. We don't know. We can do it in R. There is an inbuilt function that is called t.test. Funny enough, this function can do it for us. It can do it. Yeah, well, sorry about this. I actually missed this little example, which was just to make the point, which is an important point, of course, that even though 95% confidence interval, sort of globally, somehow is the default choice, If you look at scientific papers across all areas around economics, health science, engineering science, or whatever, people will use 95% confidence intervals almost exclusively. But you could, if you want to be more sure, if you put that in the contract with the people you work with, it's a contract you make between two. Before you do everything, you sign up for the risks in what you do, and you make sure that the people that you contract with is realizing what the risks are. And then we have a shared risks, it's open, and that's what we work with. We could want to be more sure, but that's easy. We just find, if I want to have the 99% confidence interval, I go for the 99.5% percentile, right? Because if I should have 1%, I should have only 0.5% out here, like this, and only 0.5% here. So sort of the percentage is sort of split between the two tails, right? Like this. Which means that this is then the 99.5 percentile, because it has a 0.5% to the right of it. I look that up in my t-distribution. Now it's no longer plus minus 2. Now it will be larger. For instance, plus minus 3.25 times the noise. Think about that. If you want to be more sure that you're right, you have to pay for it by providing a larger interval, right? Maybe at first sight it seems a bit counterintuitive, but I think if you say it like that, I hope it sounds pretty reasonable. Certainty, if you want to be very certain, you have to go far out. If you can live with a high uncertainty, you can give a narrow interval, right? And then to show that you can get this from the t-test function in R. The t-test function also shows this default 95%, because if you don't give any confidence level, it will default use 95%. As I said, that's the global default choice for these things. But we could just ask for something else if we want. For instance, 99%. And then it will give us something which you don't know yet. Something that I will teach you next week. But then it does give us what I just taught you. This one, and of course the mean also. So it just makes the computations for us like that. Nice. Let's do the final little Kahoot before the break. Red, t-distribution, black, standard normal. Good job. Good job. And the Mr. Positive guy or girl is on the top. To the English-speaking crowd, "Nei" means no. So let's have a break. Meet you in 15 minutes.